I wanted to cover accuracy and precision a bit more so you understand the difference between the two of them and the way they relate to percent error. That involves a bit of significant figures. We're not going to delve into that too far. Significant figures are not on your midterm, but I think that significant figures help you to understand the background of accuracy and precision and percent error a bit better. So we're going to gloss over it a bit. When it comes to accuracy and precision, what's the difference between the two of them? It's a really profound difference, especially for biological sciences. They both have the similarity that they are both qualities of an experimental measurement. They're both describing experimental measurements. We talk about how accurate a measurement is. We talk about how precise a measurement is. Two different things. Let's explain that accuracy is how close the measurement comes to a true or known value. How close your measurement comes to the well-accepted true value of a measurement, of a standard. Precision is how consistent multiple measurements are that you make. How consistent they are. And if you just make one measurement, how much detail is in that measurement based on equipment? So previously you saw a video about the differences between accuracy and precision, and you saw about how the consistency of multiple measurements really demonstrates precision, especially with the bullseye, right? But what if you're just taking one measurement? You can look at another definition of precision on how much detail is in that one measurement based on your equipment and the precision of that equipment. Let's go into it a bit more. This is easy to understand once you see it. For instance, you have two rulers. You have ruler A and you have ruler B. They look the same for color, but they don't look the same for detail. This ruler A has many ticks on it. There's the 1, there's the 2, and a longer line in between, probably in half, right? So we probably have 10 ticks here, 1/10, 2/10, 3/10, 4/10, 5/10, all the way up to 9/10 and the 2. You get that between the 2 and the 3 as well. So therefore, when you make a measurement of this arrow, with ruler A, you can say that's 2, and then you go to tenths. 1, 2, 3, 4, passes 5/10, 2.5. You can estimate the last digit, 2.5, and that looks like it's right in the middle. Okay, I'll estimate it. 2.5. 5 is the estimate, the last digit. Can you do that with ruler B? No, this piece of equipment does not have as much detail. This piece of equipment has a 1, no ticks to the 2, and no ticks to the 3. So in measuring here, I have covered to the value of the 2, so I put the 2 in, and then my last digit is going to be an estimate. And I'm going to have to estimate it right about halfway. I don't really think it's a 0.6. I think it's more like a 0.5. That's my last best measurement with this piece of equipment that has less detail. So that ruler A measures with more detail, with more precision, and oh, by the way, with more significant figures. Because we can be sure that we went past the 2, we went past the 0.5, we can estimate at a third significant figure. Here, we can only estimate with 2 significant figures. That's a very broad overview of significant figures and how it figures into precision based on your equipment. I'll give you a little bit more on significant figures. Significant figures, remember, are all about detail. So that numbers that have to do with details are known as and counted as significant figures. When you are talking about zeros that are in front, in many cases, those are insignificant figures, because if you applied scientific notation to this value, you would never include these numbers in front. So in using scientific notation on this very long number, you would say this number is 4.004500 times 10 to the negative 3. And you would have all of these digits as significant because they point out the detail that was in your piece of measuring equipment. And those are significant digits. That's a very broad overview. This will not be on the midterm, but I thought it might help you to understand precision a little bit better so that you can understand the background of what you're doing in your lab. Significant figures and precision are all about detail. And in multiple measurements, they're all about consistency in your measurements. Now, when it comes to percent error, both accuracy and precision figure in. And I wanted to give you a little bit more context on the formula that is in your lab. The formula that is in your lab is percent error equals experimental value minus theoretical value over theoretical value times 100. And that's all fine and good. You can remember this as E minus T, like ET phone home, E minus T over T times 100. But in reality, you might have a hard time in word problems separating out experimental values and theoretical values in the word problems. And in your lab, you have word problems. So I'm going to give you some vocabulary for percent error. And in this case, before we get to the word problems, I'm going to set you up for the fact that experimental value can also be known as a measured value. You did the measuring. A decided value. Your group decided that that was the value of your data. An obtained value. Maybe you obtained it from someone else. The theoretical value is supposed to be the exact standard value, the true value, the accepted value. So that's some of the vocabulary you might see in the real world and in word problems. And I wanted to point it out to you. Let me move this up so you can see it a little bit better, or I guess move it down. I'll move it down. So you have 3 word problems on your lab. I thought I'd do you a favor and tell you a little bit about the vocabulary and line it up with the colors. Now, I really hope that you will go through the PDF and go back and forth between, because these reddish areas are the accepted values, the standard values, the theoretical values in here, the actual values. And in green are some of the vocabulary for your measured values. These students obtained a mass. These students decided that the velocity was this value. these rail cars actually took 3.26 hours. Now this is tough, right? Because actually sounds like it's a standard value. You really have to read into this problem and decide which is the standard and which is the measured value by the group. I hope this will help you out. I'm not going to tell you the answers, and you have to apply the formula, but I hope this helps you with your lab. Take care.